This movie accompanies the paper providing interactive network layout in diagram editors. This is our prototype diagram editor. As in other diagramming tools, it allows the user to create and manipulate shapes directly on a canvas or to create connectors between them. This tool is unique in that it provides continuous automatic layout to support the creation of network diagrams. In this example, we're creating a flowchart, and the system is continuously adjusting and improving the layout as we work. Construction of network diagrams in this way is a collaboration between the author and the tool. Of course, the tool only has a very general notion of what makes a good network diagram layout, which is defined in terms of an optimization problem. The author can tailor the layout to suit their particular diagram and requirements by specifying constraints over the layout. The tool allows the user to specify constraints at several levels. Firstly, they select a general style for the diagram. In this case, the author has specified flow layout, which causes constraints to be generated for each connector with an arrow such that arrows are strictly downward pointing. Now the user will add what we call a placement constraint to require shapes on the main path through the diagram to line up. The third type of constraint that our system allows are called refinement constraints. These beautify the diagram by preventing overlap between shapes while preserving the topology that has been specified by the user. This next example shows interactions between characters in Shakespeare's play Hamlet. The initial layout is quite cluttered. We can turn off layout adjustment, and hence the refinement constraints, for a moment to allow us to more readily explore quite different layouts. Virtually all automatic layout algorithms will place the most connected nodes in the center of a diagram. Usually this is a good idea, but sometimes, as in this example, a better layout can be obtained by placing the 4 main characters on the boundary of the network. The author achieves this by using placement constraints to fix the relative positions of those characters. This is a good example of how human and computer collaborate together to produce an aesthetically pleasing layout. At this stage, we have a rough idea of how the layout should look. We'll turn layout adjustment back on, called beautification here in the tool, and use direct manipulation to further improve the layout by removing unnecessary crossings between connectors. You can see that now, as we manipulate shapes on the canvas, the basic structure or topology of the network is maintained unless explicitly changed by the author. Layout adjustment has a simple, rather natural physical metaphor in that the connectors behave like rubber bands. Notice how layout adjustment relieves the author from updating the placement of other objects in the network after they move something. The tool's interface is designed to make it as easy as possible for the user to create a feasible set of constraints over the layout. However, it is possible for the user to specify systems of constraints that cannot be solved. Here the user has tried to add a placement constraint that violates a downward pointing connector style constraint. The system reports this to the user by changing the color of the affected shapes, and the user is then able to resolve the conflict manually. You briefly saw the author then change the layout style. In this next example, the author will experiment with different layout styles for another diagram. This layered layout style uses an external layout algorithm to automatically generate a system of structural constraints. The user can accept the style constraints as is, or use them as a stepping stone to a better layout. Placement constraints can be added until the layout looks exactly how the user would like. The topology preserving rubber band metaphor for connectors can also be used to specify arbitrary boundaries. This communication network has a clustered topology. The cluster boundaries are treated as impervious rubber bands that wish to shrink to keep the cluster compact. The same technique can be used to create Venn or Euler diagrams to show set membership. Our final biological pathway example brings together many of the techniques already described. We've used flow layout to make arrows representing chemical reactions point downwards. We've used cluster boundaries to partition different functional regions of the pathway. Placement constraints allow us to straighten various paths through the network so that it more closely resembles the style used in biology textbooks. Extra constraints keep the diagram neatly inside the borders of the page. Thank you for watching our movie about bringing automatic network layout to diagram editors. Please refer to our paper for further details.